Let us discuss how to write an ALP for moving a block of bytes of data without overlapping, starting from the locations 30H to the locations starting from 50H. So we can write a program for n bytes. So in this program we will write for moving a block of 5 bytes of data. Okay, so we write the first statement as org00h. org00h means that your program will be stored starting from the address 00h. SJMP main indicates that we are not going to use the subsequent locations from 00h. Instead, we will be starting our program storing from 30h. So from here, the control will come to the main part. So in the main part, we use a register R0 to load the value 30h, hexadecimal number 30h. This is the source address. Similarly, we load 50h into R1 to point the destination starting address. Then we'll use R2 register as a counter to count the number of bytes. So here we are using 5 bytes, so we are using 5. If you have 10 bytes, you can write it as a 0A in hexadecimal. If it is decimal, you can write straight away #10 without H. Then you can see that followed by we have written a statement at R0. At R0 means when you use at, basically this will be used in the context of pointing registers. So R0 is having value 30. Okay, at 30H, whatever value is there, that will be moved to A register. So that is temporarily moved to A register. From A register, it will be moved to at R1. At R1, what do we have? We have 50H. So at 50H, the value from A will be moved to 50H. Okay. So that is how the data will be moved. From 30, we moved it to A register. From A register, we moved it to 50H. Then this is for 1 byte. For multiple bytes, what we have to do? We have to increment the value of R0 and R1. So R0 and R1 is getting incremented, and by using DJNZ, we control the number of byte transfer. So R2 will be decremented, and it will be checked whether it's equal to 0. If it is equal to 0 means we have reached the maximum count. If it is not equal to 0, then we can go on continue the operation. Okay. So after doing this, after writing the program, just right click on the ASM file and build a target. So when you build a target, it should be 0 errors. So 0 errors is here. Then you can start your debugging by selecting here. So by then there is a warning, just select OK here. So here you have a memory window, and we are using the internal memory. Okay, so you can write I30H. So I30H, if you write here I colon 30H and press enter, you'll be able to get the memory locations. So what do I do now? I write a value 10, 11, 12, 13, 14. Okay, so the 5 values I have given here. So A, B, C, D, E at 30H, and here this is 5AH. Okay, so this is 5A. 5A means what? This is 49, isn't it? 49. So then for 5A, then what do you have? No, this is 59, and this is 5A, 5B, 5C, 5D, like that it will keep going. So somewhere here we will be having a value 50, isn't it? Down the line, if you look into it, you will be having 50. So those 50 locations currently now it is having a 0 value, isn't it? Okay. So now what you do, before running the program, this is the status. Now we will run the program. To run the program, select this icon. So when you run the program, you can see that the data from 30H, it's moved to the starting address to 50H. All the 5 bytes are moved. A, B, C, D, E we have 30, 31, 32, 33, 34. Whereas now in 50, 51, 52, 53, 54, we have the value A, B, C, D, E. So like this, by varying the value of R2, we would be able to configure this program for moving n number of bytes. The next part of the first experiment is writing an ALP for moving a block of bytes of data starting from one particular location to the another location with overlapping. So what does it mean? There will be some data already in the destination location. What we have to do, we need to overwrite on those data and we have to copy the new data. Okay, so now let us see how to write a program for this. So here what do? We write the org statement and SJMP main statement org30h. So these three statements, this is basically an assembler directive, this is a mnemonic. So these three statements, it helps us to mention the starting address of the program storage. Okay, then after that what happened here, see in the previous program what we have done, we have started from the first address we have moved. Okay, so now what we will do, instead of starting from the first address, now we will go to the destination address. So from the destination address we will take the bytes and we will fill it. That's how we are going to do the work. So R0 is loaded with the value 39H because we are going to move 10 bytes of data. So if the starting address is 30H, then ending address of the source location will be 39H. So we move the 39H as the last address of the source into a register R0. Then we are going to load this A with the value 5 because we have to prepare the destination address. We have to prepare the destination address. So we are loading A and 5. Now A is loaded with the 5. Then what do? We add the content of 3, 9 and 5. So when you add the content of 3, 9 and 5 in hexadecimal, it will be 3E. It will be 3E. So 3E is the number that's stored in A, and we are doing this to generate the destination address. Now the A is whatever the A, that is 3E, it's moved to R1. Then to control the number of operations, we have the R2 register. So that is loaded with the value A. What does it mean? It is going to move 10 bytes of data. Going to move 10 bytes of data. Okay. Now here you can see that move at R0. At R0 means what? In R0 we have 39. That's from the source location. Because as I told you, from the end of the source address we are going to take. So 39. So from 39 whatever the value is there, that will move into A register. Then once that is done, then the A register content is moved to at R1. What is there in R1 now? We have created a new destination address, that is 3EH. So to 3EH the value will be moved. Since we are coming from the backwards, so it is going to be decremented. R0 and R1 is decremented. So 39 will become 38, 3E will become 3D. And to control the operation, we have DJNZ R2. So this is going to continue, it's going to execute here until this R2 becomes 0. When R2 becomes 0, the number of bytes are moved from source to destination location. So after writing a program, right click on this ASM file and build a target. After building a target, then you can go for debugging. Okay, so in debugging, and here I have, as I told you, you can enter I:30H and you can enter that. Then starting from here, I am going to use 10 bytes of data. So right click on this and select modify memory element. Then enter the values 1 in decimal, 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. So it will store a value 1, 2, 3, 4, 5, 6, 7, 8, 9 A. And now we are moving from 30 to 39 to the address starting from 35 to 3E. That's the basic intention. So from 39 we are going to take the value and we are going to move it here. Okay. So you can see that here before execution 1, 2, 3, 4 like that. After execution how it would be? First 5 bytes will be remain as it is. From 6 it will become 1, 2, 3, 4, 5, 6, 7, 8, 9, it goes. Let's see how it's going to come. You can see that now here. So previously we had some bytes stored here in this particular memory location. Now with this writing, what we have written? We have overwritten the contents of this memory area. So you can see that 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8, 9, 8. Again, by modifying this, we can modify the number of bytes to be moved from source to the destination location. Okay. This ALP program is for exchanging the contents in the memory locations. Okay. So here we have two memory locations, 30H and 50H. So starting from 30H, we have 5 bytes of data here, 5 bytes of data. Then starting from 50H, we have another set of 5 bytes of data. So before execution, both the locations will have the value 5 bytes of data. So after running the program, how it should be, the content from the starting from 5 contents, 5 bytes, starting from the address 30H should be moved to 50H, starting address 50H, and similarly what was there in 50H should be moved to 30H. Got it? That's what we call as an exchange. So how do we do it? So we have the assembly directive, we have the main address that is starting from here, then we have the R0 loaded with the value 30H. So that points to one location, that's a source location. Then R1 is loaded with the value 50. So we use two pointing registers, R0 for 30H, R1 for 50H. So both will be pointing to different places. Then to control the operation, we have 5H here. That's loaded to R2. Then at 30H, whatever value is there, that will be moved to a register. Then for using a instruction, straight away an instruction called XCH, called exchange. What we can do, we can move the content of A, or we can exchange the content of A with the content of the address in R1. So what is there in R1? We have 50H. So at 50H you have some value. Then A is already having the value that was in 30H. So these two contents will be swapped. After swapping it, next what we have to do, we have to move the value that is taken from 50H to the 30H. So again we write a statement, move A, at R0. Then increment the count of the registers R0 and R1. Then by using R2, we can count the operations. That's the basic law. Again, by varying this count, we can enable the program or configure the program for multiple bytes. Okay. Now, there's the program. Right click on the ASM file, then build the target. As build target, ensure that errors are 0. Then start your debugging. Once the debugging is started, then select OK. Then again we are using for 30H, right? So what you do, from here you can enter the values, 5 values, 1, 2, 3, 4, 5 I have entered. So 1, 0, 1, 2, 3, 4, 5 is entered here. And also we have to enter the value in 50H, isn't it? So value in 50H. So when you enter the value in 50H, what I'll do, now I'll make it 10, 11, 12, 13, 14. So 5 values. A, B, C, D, E will be there. Now if I take the value here again back to 30H, I would be able to see that 30H is starting with the 30H, you have the 5 values here, 5 bytes. Starting from 50H, you have another 5 bytes here. So here we have 1, 2, 3, 4, 5. Here we have A, B, C, D, E. After execution, what it should do, this 1, 2, 3, 4, 5 from here, it should come here. This A, B, C, D from here, it should go to 30H. Let's see it's happening. Just run the program. You can see that from 50H, the 5 bytes moved to starting at this 30H. Then from 30H to 50H, 5 bytes are moved here. 1, 2, 3, 4, 5. Good. So by varying this counter value, we can configure this program for n bytes of operations. This program is meant for writing an ALP for sorting the numbers in ascending or in descending order. So first we will write for ascending order. The same program can be easily configured for descending order. And this program is written based on the bubble sorting algorithm. Okay. So here, now what we have here, we have the ORG 00H, SJMP main, ORG 30H. This is an assembly directive, mnemonic. Together, it helps us to decide the program storing the address. Then what we have here, we have the two registers, R3 and R2, loaded with the value 9H to control the loop operations, inner loop and outer loop. Then we are going to store the number sequentially in ascending order in memory. So to access the first address, we use the first address 30H and loaded into R0. Then second location 31H is loaded into R1. So from R0, we take the value and move it to A register. So what is the at R0? That is at 30H, whatever value that move to A register. And at R1 means at 31, whatever value that move to B register. Then CJN is an instruction which will compare and let us know whether the number is going to be, the first number is greater than or smaller than the second number. So if the first number is smaller than the second number, then it will set the carry flag high. So the condition of the carry flag can be seen by using the conditional jump instructions called JC, JNCs. So now here, when the comparison statement checks the conditional contents of A and B, and if it is not equal, and if it is greater, okay, if it is greater value, the first value is greater than the second value, then what will happen? It will go on checking it. Got it? So it will come here, JC, no exchange. So here it will check whether the carry flag is set or not. If the carry flag is not set, that means this condition is not satisfied, the first number is greater than the second number. Then what we'll do, we'll exchange the content. So whatever is there in R1, we'll move it to, we'll exchange it with the A, and here we move it back to the first location. Then what we have the content R0 and R1 that gets incremented here. By chance, if it is smaller than, if the first number is smaller than the second number, then it will go for no exchange. In no exchange, we do not do any exchange operation. Straight away we increment the R0 and R1 value. And also, to implement the bubble sort algorithm, first what we do, first we will compare the numbers. If it is greater than the first number, then we will go for incrementing, isn't it? So that operation need to be continued for different iterations. So we have two iterations to be done here. So we have the first iterations here. So for the first iteration we use R2. For the second iteration we use R3. So when after completing this only, then the second iteration will start. The second will take the control from here to here. So after executing all the program, then microcontroller will come to this place and it will continue to execute this particular statement. Here SJMP, here. Okay. Now let us build the target. So if we build the target, we will get to know there are 0 errors, and you can start your debugging. As you start the debugging, then the contents are refreshed here. So what do I do now? I just give the number randomly 9, 5, 7, 2, then kind of then what will give? 1 I will give. Okay, then click OK. So 9, 5, 7, 2 like this. So after ascending order, it should be 1, 2, 3, 4, 6, 9, isn't it? So actually this program is written for 10 bytes, so we will get 10 bytes now. 10 bytes I'll give. So 2, 5, 9, 7, 6, and another 4, okay, 1, so 6, 7, then 8, then again we can give 9, and also we can give 10. Okay, let's see how it's going to perform. So like this, the randomly values are going to be loaded, values are loaded here. Then when you run the program, what you can see, you should be able to see that it's stored from 1 to 10 in ascending order. Let's see that, where it is in the same location only. Okay, you can see that now the contents are arranged in ascending order 1, 2, 3, 4, 5, 6, 7, 8, 9, 8. Okay, this is for ascending order. To configure the program for descending order, what do we do? This JNC is there, JC is there, that will move it to JNC. So that means what? When the carry is not set. That means when the number is, the first number is greater than the second number, then no exchange. If the first number is smaller than the second number, then there will be an exchange here. Okay, so that's how it is done here. So after doing the changes, you save the program, then again build a target. So build the 0 errors, then you can give the program, start the program, and click OK. Then now what do? I give in ascending order value here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. After giving this, if you run the program, it should go in descending order, A to A, 9, 8 like that. It should continue to go. You can see that A, 9, 8, 7, 6, 5, 4, 3, 2, 1. It is sorted in descending order. Okay. So here, by varying these two R3 and R2, we would be able to control the number of operations. You want 5 bytes to set in ascending order, then you can change this to 4. Okay. If you look at the bubble sorting algorithm, then we can easily understand the execution of this particular program. This program is meant for finding a largest and smallest number. First, let us see how to work for largest number, then we will see how to find a smallest number by modifying this program. Okay, now here, so the concept is there will be a number of bytes stored in an array. First, we will take the first byte. If the first byte is smaller than the second number, then we will keep as it is. If the first byte is greater than the second byte, then we will swap it. Then subsequently we will do this comparison. Finally, we will get to know whether the number is greatest, what number is greatest. Okay. Now here we have 30H loaded into R0, 31H is loaded into R1, Then to control the operation, we have the R2 loaded with 4. So by using this, we will get to know this is used to find the largest number of the 5 numbers. Largest of 5 numbers. Then at or not, whatever there in 30, it's moved to A. Whatever there in 31, it's moved to B register. Now the comparison takes place. A first number is there in A register, second number is there in B register. When it compares, then we check for the carry, because the carry will let us know whether the first number is greater than or smaller than. If the first number is greater than the second number, that means the carry will be 0. So by using this JC, we'll get to know that when carry is 0, we'll go for exchange operation, so the numbers will be swapped. When carry is equal to 1 means if the first number is smaller than the second number, then what we'll do, we'll go for the swapping, isn't it? So then we'll go for the no swap. So here we have INC R0, R1, then also we have the DJNZ R2 here to control the operation. So by controlling this operation, we can find out how many bytes can be used for sorting the numbers and also to find the largest number of the n numbers. Okay. And also we have we can use this program to find the smallest number as well. First, let us simulate this answer. Right click on the largest number, then build a target, then start your debugging. So started debugging, then you can give any values. You can see that we have used the port also here, P0 at R0. Okay, so whatever there in the at R0, that will be the number that we will take it to for P0. So separately we will show here the largest number here. Okay. So what do we have? The numbers we can enter it here, any numbers. Can enter 1, 5, 3. So 5 numbers I have entered here. So this will find the largest number. So largest number means the 8 should come to 4 P0. So now just run the program and see that. You can see that since the program is written for sorting also, so it will sort it and also it will bring the value, the last value 8 into this 4 P0. So this gives the largest number. How to configure this for a smallest number? So stop your program and also you can just stop your debugging. You can go here and change this JC to JNC again. So then save the program, then build a target, 0 error, then go for debugging. So in the debugging, now we'll enter the value here, any values, 5, 8, 6, 2, okay, 7. So now that is entered here, 5, 8, 3, 4, 7, value is entered here. Just run the program. This will give you the smallest number. That is, smallest number is 3. You can see that the smallest number 3 is displayed here in the 4 P0. So by configuring JC and JNC, we can configure this program for finding the largest number or the smallest number, and also by using the R2, we can control the number of bytes involved in this operation.